Hello guys, this is CodeNCode and this is video editorial for the problem and zero big sum taken from Codeforces Div 2 round 716, and this was a B problem. So the problem statement is pretty simple. You are given two integers n and k, and you have to find the total number of arrays of length n such that each element of the array lies in the range 0 to 2s per k minus 1. For example, if k is equals to 3, so each element lies in the range 0 to 7, right? Bitwise AND of all of the elements should be 0, and sum of all of the elements should be maximum possible, right? So we have to find how many arrays are there of length n such that they follow all these three conditions. And since the number can be pretty large, we have to print it modulo 10 power 9 plus 7. This is given in the problem description itself, so you can go ahead and read that. So example, if n is equals to 2, k is equals to 2, answer would be 4, because there are 4 arrays of length 2 such that they follow all of the three conditions. So if you see, I've represented them in binary numbers. So this is the first number 3, their AND is 0, and maximum sum that you can achieve is 2 raised power k minus 1. I mean n minus 1 times 2 raised power k minus 1. Why is that so? I'll be proving it later. So n minus 1 is 1 times 2 raised power k minus 1, which is 3, right? So 3003 1221. If you perform AND of this, result is 0, AND of this, result is 0, AND of this, result is 0, so on. So all of these three arrays follow all of these all of these four arrays follow all three conditions. That's why the answer of test case 22 is 4, right? Now, first observation, the maximum possible sum that you can achieve, that an array can achieve following all of those three conditions, is n minus 1 times 2 raised power k minus 1. So if n is equals to 5, and of course n is equals to 5 and k is equals to less than 3, then 4 times 7, that is 28, is the maximum result that you can achieve. How? Let me show you with an example. Here, suppose n is equals to 5, so we have 5 integers, right? And these are their bits. I'm assuming they are 8-bit integer. Basically, I'm assuming k is equals to 8. See, when what this represents is actually k represents number of bits, right? Why? See, it says that the elements of the array can be at max 2 raised power k minus 1. When you take an integer 2 raised power k minus 1, it has all the bits from 0 to k minus 1 bit. Basically, you have k bits. So k actually represents number of bits you can have. Okay, so suppose n was 5 and k was 7, right? Sorry, 8. So we have 8 bits, and these are all of the integer, and these are their bits. For a, this is it is its 0th bit, it represents its first bit, and so on, right? So for each of the number, these are their corresponding bits, corresponding ith bit, right? Now if since the second or third, one of the statements says that their AND should be 0, right? When you perform AND operation, so 0th bit should, all of these bits should result 0, right? And 0th bit are AND with 0th bit, right? They do not interfere with others. So the AND of all of these bits should be 0, AND of all of these should be 0, and so on, right? That means one of the bit must be 0, right? You can't have all of them 1, you can't have all of them set, right? One of them must be 0. We can have more than one, but since we have to maximize the sum, we can only have one bit set, and the result would be 0 out of all of these 5 zeroth bit, right? Similarly, for 5 1 bit, we can have any one of the 0, and the overall result is going to be 0. So out of all of these, one should be 0. Out of all of these, one should be 0. Same goes for any bit, right? I want you to understand this fact at this point at least, right? So what the point is, what I can do, I can make all of these bits 0, right? And all of the rest of them 1. So this is 0, all of them is 1, this is 0, all of them is 1, this is 0, all of them is 1, because we only need to make one bit 0 in each of the column, right? So I've set all of these 0, the rest are 1. So if you see, this integer would result into 0, and all of these would result into 2 s power k minus 1 because we are using k bits. All of the k bits when are set, the result is 2 s power k minus 1. So the overall result would be, since this is 0, the n minus 1 elements are 2 s power k minus 1. That is why the result is n minus 1 times 2 s power k minus 1. And this is not the only possible configuration, setting all of these bits 0. This is one of the possible configuration. So let's go ahead and see what is the second observation, that is, what is the answer? How many arrays are there which fulfill all of the three conditions? The answer is n is power k. Why? Let's see. So let's see how many different configurations are there. So see, this is one of the configurations that all of the bits of the first integer are 0 and all of the bits of all the rest n minus 1 integers are 1. So all of these you see are 1. This is 0. Now do you think what would happen? Just think what would happen if I swap this bit with this. Basically the 0th bit of first integer becomes 1 and the 0th bit of second integer becomes 0. Basically I'm swapping this with this. What would happen? What will be the total sum? Just think. See, the total sum, this integer would reduce, a2 would reduce by 1 because this bit initially was 1, now it is 0. So it would have a loss of 2 s power 0 because this is the 0th bit, right? So this would reduce by 1 and this is increasing by 1. Rest of the integers are same, so the total sum doesn't change. This is being reduced by 1, this is being increased by 1, so the total sum doesn't change, but this leads to a different configuration, right? So that makes a new array, which means another configuration, right? So now we have two different configurations. Just think what would happen if I swap this with this. The same thing happened. This would reduce by 1, this would reduce by this would increase by 1, and we have new configuration. Now these two are now 0 is placed here, not here, so we have one more configuration. So you see, same way you can swap this 0 with any of the bit. Basically the position of 0 can be anywhere from the first integer to the nth integer. So this can take place, this can have n different configuration, this 0 can have n different places, which will lead to n different configurations. Same goes for this bit. This bit is not special. Same can happen with this bit as well. You have placed this bit here, 0 here, you can replace this with this, right? And it would lead to a different configuration. Same way this 0 can have n different position, similarly for this, similarly for this. So the total number of configuration would be n times n times n times n dash 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 till k. So if you take product of all of these n, which are k times, the result is n raised to power k, right? And that's how we have n raised to power k different configuration. Again, each bit can be swapped with the remaining n minus 1 integers, right? Each 0th bit can be swapped with n minus 1 different integers. Basically, ith bit, the 0 at the ith position have n different places. Same goes for any other bit. So n possibilities for this times n possibilities for this, so on and so forth. There are k different bits, so total number of configuration would be n raised to power k. This is simple combinatorics. That's why the answer is n raised to power k. If I show you the code, here you see I'm simply reading n and k and printing n raised to power k modulo 10 to the power 97 of course here, right? How I'm calculating it, I'm using binary exponentiation, which will calculate the result in log n time, and that's how I'm solving this, right? So this is the solution of this problem. There's nothing more here. If you have still any doubt or query, you can ask in the comment section. So this was all for this lecture. Thank you guys for watching. Until the next video drops, keep coding. Thank you.